Hello, everyone. This is Terry Erzman. I'm organizing the webinar for today. Welcome to today's webinar. Before we get started, if you could please raise your hand in the GoToWebinar control panel if you can hear me. Just make sure our sound is good. I see some hands going up. Thank you very much. We will be recording today's webinar, and we'll send out a link to the recording as well as to the slides within the next 24 hours. So please watch for that in your inbox. Feel free to share that with your colleagues. If there's any questions, please feel free to email us with questions following the webinar. If you have questions during the webinar, please enter them in the questions box in the GoToWebinar control panel, and we'll answer as many questions as we have time for at the end of the presentation. With that, I will turn it over to Alexei. Alexei?
Yes, thank you, Terry. And hello to everybody who's on the line. So my name is Alexei Goncharuk. I'm an architect at GridGain Systems, and today I would like to talk to you about the best practices of loading data to distributed systems changing the capture. This is going to be a recap of my talk at the In-Memory Computing Summit in San Francisco, with probably a bit of small additions. Let's check what we're going to talk about today. So first of all, I would like to check with you what we mean when we talk about the change data capture. Then we will see what tasks and what use cases we can solve with the concept of change data capture. And in the end, we will see what tools and what approaches are available in Ignite and GridGain, which APIs are there, and which restrictions or benefits each of those APIs can give to you. All right, what is change data capture? The task definition that I would give for the change data capture is, so let's say you have a data set of arbitrary size. It can be a relational table, it can be a key value data store, it can be a document store. And at any moment in time, you want to determine what records have changed since a given moment in time. And obviously, there are many ways to achieve this, and we'll walk through at least several of them, which are widely used in production and are available in many systems. First of all, is a concept which I called record change markers. Essentially, a record change marker is maybe a timestamp, maybe a version, maybe a status, or something else, which you can attach to your application data model. Let's check an example. So here we have a table which has several rows. I omitted the actual content of the table because it doesn't really matter what content of the table is. For us, it's important to know that we have IDs of rows in this table, and we also attached a separate column which I called update timestamp. And what you do when you update the table or insert some rows in the table is you basically capture the current moment and insert it into update timestamp column. So let's say this is the state of our table, and then at some point in time, we've updated records with ID 4 and 10. So now, let's say we want to know what changed in this table since, for example, midnight of February 12, 2012. The way we can do this is just execute this simple query. And this query will give us all the rows, or we can select only row IDs that have changed since the given moment in time. So this approach is straightforward, but it has several negative features, if I may say. First of all, detecting changes may be tricky because you either will go to a full scan for the table if you want to see which records changed since the given moment in time, or if you want to have faster queries, you would need to have an additional index for the edit column. And additional index means that you spend more space or spend more memory to store the index, and it will also may affect your performance when you do updates or inserts to this table. The other consequence is when you update the table, you essentially override the previous state. So now when we select the updated records, we only see the new value. So the previous value or the number of changes that you saw or you missed since the last scan is essentially lost. The pros of this approach is that even if the system that you use doesn't have any concept or built-in mechanism for change data capture, you can still implement this approach and capture the changes from your system. If your application which receives the updates from your system is not online, you can still read the updates at some point in time later, because all the data all the change markers are there, and you can consume the changes as many times and at any moment in time in the future. And if you don't use indexes, then storage overhead for this approach is negligible, because usually change marker is a timestamp or simply a flag, and compared to the size of the row, it's really small. Okay, let's go to the second approach to CDC. It's callbacks, or in some, probably most of you know that traditional database systems provide such things as database triggers. Or, for example, in Apache Ignite, a callback is called an interceptor for reasons that I'll cover in a few minutes. Usually, when we work with callbacks, it means that we provide the storage system or the database some sort of user code that is supposed to be run. For example, in Apache Ignite, it may be Java code. When you run a traditional database, it may be a stored procedure or some piece of code that you write in TLSQL, for example. Schematically, this can be pictured this way. So when an update happens in your database, the system executes the user-defined action. And then once this action is executed, the update finally propagates to the underlying storage. Let's see what cons and pros this approach has. First of all, we take it as a con. The callback is invoked synchronously, which means that if you want to run some heavy computational logic or do, for example, a external system call, a callback may not be the best solution, because it will affect the insert to update performance. When we talk about a distributed system, callback is also tricky to handle with respect to failover, because if your callback has any side effects, things become very complicated, because in case of failover, your callback may be executed more than once. And in this callback, you need to make sure that the actions that you run do not cause any duplicates in these side effects or in any external system you communicate with. As for the pros, essentially when you have a callback or a trigger or an interceptor, you absolutely have no storage or insert overhead. So if your trigger or interceptor runs fast enough, the performance effect is negligible, and you don't add any additional storage space or columns to your model. Usually, previous value is available. In some systems, it may be configurable. For example, if your system is using something like LSM, a optimized storage engine, the previous value may not be immediately available, so the previous value lookup may come at additional cost, but usually previous value is available. As a result, since the trigger or interceptor invoked synchronously and the previous value may be available, you have an ability to actually change the value that will be finally propagated to the underlying storage. For example, you can encrypt or decrypt some data if the system doesn't support the encryption out of the box. Let's go to another way of CDC. It's personally my favorite one because it's very flexible. The approach is called the change feed, and conceptually it can be described as the changes are stored as event. We can use the term event sourcing here, or the changes produce events, and those events are either written to the disk or kept in memory until they are consumed. After we produce these events, consumers may subscribe to a change feed and read either the full feed or the portion of the feed, or filter out events that the consumer is interested in. And we can note that if you use a database with red hat logging, essentially the database red hat log is an event source that we can use, and many well-known databases like Oracle use this approach. So probably if you use Golden Gate, underneath they doing something very similar to reading the database journal. So essentially, the update that goes to a database goes both to the stable storage and an additional journal, which can be a part of the system itself. And later, this journal can be read by subscribers. This approach has very few cons. Well, you need additional storage to keep those changes, but again, if you're using a traditional database, usually those changes are already written to the disk for the reasons of crash recovery, and normally you would not turn that off. As for the pros, since the red hat logging usually has both redo and undo changes, the previous values are available. If you have enough disk space, the full change history of your system may be preserved. So for example, if you have a snapshot of the data, and then you have your journal, essentially you have the whole history of your data changes since that snapshot or since the beginning of the times, if you have enough disk space. And of course, unless you delete those files or wipe them from the memory, in case of an in-memory system, you can reread the history as many times as you want. And this replay can stream the data changes in as many times and in as many systems as you want. Now let's switch to the more interesting part of this talk, is the applications of change data captures. Now that we know how we capture actually the changes, let's see what we can do with this. The first approach is continuous data integration, and it essentially may be thought of as active and passive, active-passive replication. So you have an active database that, or data storage that produces changes, and the changes are applied to a secondary system. And the way both of the systems produce or consume events, actually here it doesn't matter. So those systems can be of different types. So you can do change the capture, for example, from Oracle to Ignite, or from Ignite to some archival storage like something based on HDFS. And etc. So schematically, we have an active system, we have captured changes, and we have passive system. And the reason why it's easy is the changes always flow one way. So you don't need to worry about possible conflicts, as we see for the another CDC case in the future. What continuous data integration can be used for? First of all, it's reads offload. So when you have an active cluster, for example, that is used to process transactional data, then the passive cluster can be used to serve maybe a little bit stale, but still very close to the actual data. So if you have some analytical reporting, and this is probably a usual use case. So for example, if you have a active system that currently processes transactions and you want to do fast queries in Ignite, you can configure change data capture to Ignite and run SQL in memory, and only keep in Ignite the actual operative data set. Another use case that we actually saw one of our customers to implement is audit changelog. So essentially, every update in Ignite cache was captured and stored to a local file system journal, and eventually transferred to a centralized table storage. And this way, if some unexpected update happened in Ignite, the audit changelog would immediately display this change, and our customer would see which subsystem introduced this change and what the previous value was. And the third application is the cross-system replication. Is if you, for example, if you're migrating for an old implementation to a new one, you still, of course, can use this approach. And of course, high availability, but for the high availability, you would need to ensure that the reads that are served from the passive system can tolerate the time lag, because usually the change data capture implies that the synchronization is asynchronous. The second example of CDC application, I actually really love this example because it's not so widely used, but from our experience, if you actually know about this approach, you can have very significant performance improvements in some cases, and sometimes people forget about this option. The example that I want to show is running function calculation, but the concept actually can be applied to a wider spectrum of use cases. So let's say you have a computationally expensive function which consumes all the data set to produce result. If you can decouple this function in such a way that you can calculate an initial state, and then once the changes come, you can update this result, you would only need to update the results each time the data changes, and then you can query the result as many times as you want without need to rescan the whole data set. As an example, let's take a pretty simple task. Let's say we want to calculate the average of some column in some table. Essentially, the average is a sum of the item values divided by the number of those items. And if we calculate average without any preparation, it will always take big O of n complexity because we need to sum all the values from our dataset. But let's say we calculated the initial state of our running function, we calculated the sum, and we calculated the number of items we have in our dataset. Then we will set up a change data capture routine. It can be an interceptor or it can be a change feed. And then we will update our intermediate results. When we do inserts, we will update the sum and we will plus the new value and increment count. When we delete, we will track the deleted value and we will decrement the count. And on update, we will update the sum and leave the number of items the same as it was. Once we get this simple routine installed, our average will become a constant time operation because the sum and the count, the number of items, is already calculated, it's up to date, and we will just need to divide the sum by the number of elements. And again, this is just an example. And if you can decouple your task into initial data scan and incremental updates, it may significantly change the way your query works. Of course, we need to understand that actually we move some of the part of the data of the query calculation from the initial query to each incremental updates, So for example, here on each insert, we will update the sum and we will update the count. But usually this trade-off is worth the speed up that we will get on a query. And for the cross-system active-active replication, again, the same approach can be used as with active-passive system replication, but now the update feeds are going both ways, so from one system to another and backwards. And in case if a row with the same ID or a key is updated simultaneously in both systems, now we have to resolve a conflict. And usually it's not a very simple task because conflict resolution depends on the business logic that you would have in your application. But usually there is an approach that may be suitable for a good portion of the use cases by default. The approach is called conflict-free replicated data types. I think the topic is quite large, and probably we will do another webinar or set up a talk or a meetup about the CRDTs. And for now, I will just cover some of the basic CRDTs that are there, and you can look up the information because it's widely available. So first of all, the first CRDT, which is very basic and quite easy to understand, is a grow-only counter. So essentially, you increment a register in your cache, and when you get a conflict, you always select a maximum value, since it's a grow-only counter. A positive-negative counter is essentially a pair of two grow-only counters. So when a conflict appears, you select the maximum of the corresponding counterpart of the pair, and the value of the positive-negative counter is the first value minus the second value. So it's counter that can both grow and shrink, but still the conflict resolution is possible. A more complex but still quite easy concept is grow-only set. Now, instead of a counter, you have a set which captures unique values, and you can only add values to the set. Now, in case of a conflict, if you have two sets, you can get a union of the values that are present in both of the sets. Two-phase set is an analogy to positive-negative counter. You have two of the sets, and on conflict, you take union of the counterparts, and a result of the set is a first set minus the elements in the second set. I think the last right wins strategy is one of the most popular for the conflict resolution, but in our experience, it may be a little dangerous, because once you, essentially last right wins means that you attach a timestamp to your data, and doesn't matter which kind of data you replicate with CRDT. And when you get a conflict, you choose a value with the latest timestamp. The caveat here is that you need to somehow synchronize clocks on both sides of the replication process. And it's really hard to do. And if you don't want any unexpected conflicts, you probably don't want to use the last right win strategy. But if sometimes you can assume that more recent right can be overwritten with a less recent right, it may be one of the easiest strategies to implement. And there are some of them more complicated, which again, you can look up on the internet. Okay, now let's switch to the tools and APIs which are available in Apache Ignite and what we can do with those APIs. We'll start with the task of applying changes to Ignite, since luckily it has only one solution which is very effective, and the solution is called Ignite Data Streamer. The main task of Ignite Data Streamer is to optimally deliver changes to data nodes. So by default, the data streamer will write changes to caches, but optionally you can implement your own stream receiver. And this way, data streamer will take care of optimal delivery of the data batches to primary nodes. And then on primary nodes in the stream receiver, you may execute any particular logic, because stream receiver is just a Java interface which you can implement. We may combine Ignite Data Streamer with several solutions such as Kafka or MQTT and a lot of others which are already available in Apache Ignite. And these integrations basically, with a few lines of configuration, allow you to plug your CDC stream from another system to Ignite. So you set up, for example, Kafka. You set up Kafka sync in Apache Ignite. In configuration, you just connect those two pieces, and the flow of updates will go to Apache Ignite. As for Ignite as a streamer, the only thing you need to take care for now is that right now data streamer does not ensure the order of the updates which are put to the stream receiver. So you need to include some sort of version or status check into cache update when you're applying the changes, because otherwise the updates may be reordered. However, we've received a lot of change requests about this shortcoming in Ignite Data Streamer, and hopefully at some point in the future we'll introduce a mode for Ignite Data Streamer that will ensure the update order. Now let's see how you can actually capture the changes in Apache Ignite. The first approach that we've talked about, other than the update markers, is callbacks. And in Ignite, you'll have essentially two kinds of callbacks. The first one is cache interceptor. Of course, it updates, it guarantees update order because it is invoked synchronously, as we may remember, and the interceptor may alter the inserted value. So using the cache interceptor, you may, as in my previous example, you may encrypt and decrypt the values that are stored into Ignite cache. But again, you need to remember that it's synchronous, so it may affect performance. And since it's executed in a critical section of key lock, during the time the interceptor is executed, all other updates on this key will be blocked. Another callback that you may have in Apache Ignite is cache events. They still guarantee update order within each key. They are asynchronous. So you need to remember that since they are asynchronous, an additional care should be taken when you execute logic with side effects in distributed system, because in case of a node crash, an update may already have happened, but your callback may not get to execute yet. And finally, if we combine callback and change data feed, you will get an API in Ignite, which is called continuous query. Continuous query is essentially a client-server subscription, which captures updates on data nodes, if we say more specifically on primary nodes, and send those updates to clients. Continuous query consists of two parts. The first part is called a remote filter, and the remote filter is installed on all data nodes, and it may filter out events that are not interesting for a client. The second part of the continuous query is called local listener, and the local listener is executed on a client or a node which actually executed continuous query. That's why it's called local. So the local listener is always local to the node which has executed the continuous query. Here I prepared a short example of how continuous query may execute in Apache Ignite. So here we have two nodes and a client which is named consumer. the client executed a continuous query and installed a remote filter on both of the nodes, because continuous query installs remote filter on all the data nodes for each cache, for a cache for which it get executed. Let's say we have update on the first node for key 1, and remote filter gets evaluated and returned false. This means that this update is not interesting to the client, and the update will not be sent to consumer. Now, if we have another update for key 2 happened on the second node, the remote filter accepts this update, and the update gets sent to the consumer. What we get from continuous queries. First of all, it's automatic failover in case of primary node crashes, which means that even if your primary node crashes, the changes that were applied to partitions for the crashed primary nodes will still be sent to your clients. So as long as you have live nodes for each partition, your change feed for the whole cache will be actual. As far as the ordering guarantees go, the updates are ordered by single key, but for now, even if you use transactional caches, the updates are not batched into transactions. Perhaps at some point in the future we will make this improvement, but for now it's not clear for us if it's a change that it would benefit a lot of users. Okay, let's recap on the tools that we've covered here. For ingestion, you use Ignite Data Streamer. So it's a tool that can optimally deliver changes to your data nodes and put updates to your cache or execute a custom stream receiver. For capturing changes, first tool that you can use is Cache Interceptor. It's invoked synchronously. It may change the values that are inserted or deleted from the cache. So in Cache Interceptor, for example, you can even check for some invariants and prevent a delete to happen. You have events which are asynchronous counterparts of Cache Interceptor. They usually have probably better performance in terms of change data capture, but you need to make sure that your business logic will be fine if update happened, node crashed, and your event callback never got executed. And finally, you have a continuous query, which a combination of interceptor and change data feed, which allows clients to subscribe to changes in Apache Ignite and consume updates that happened in the cache, optionally by filtering, optionally filtering those remote events using remote filters. Of course, since I have this opportunity, I would love to say that Ignite is open to new contributions. So if you always wanted some feature that you would love to see in Apache Ignite, but it's not there yet, you are always welcome to join the community. Here's the address of the mailing list, so you can just join the developers community, pick up a ticket or implement the feature by yourself, and do not hesitate to contact me at this address if you have any questions on the CDC approach or on Ignite in general, or any development topics related to Ignite. And yeah, I think we're maybe a little bit early, but still, let's see if we have any questions related to this talk.
Okay, thanks, Alexei. Again, if you have a question, please submit it in the questions box of the GoToWebinar control panel. Alexei, can you explain the difference between events and continuous query? In reality, both are asynchronous, right?
Yes, that's correct. They are quite similar, but events are dispatched, if I may say so, on the node, on the data node, which stores the data. So let's say, let me go back a little bit in my presentation. So let's say in this case, an update for key 1 happened in the cluster. If you used events, the actual Java code that would get executed would be on the first node. And in case of continuous query, only a remote filter that decides if the event would go or not go to the client would get executed on the data nodes. So in this case, on node with key 1 or node with key 2. And local listener will get executed on the client. So continuous query allows you to to grab all the events from the whole cluster at one point in one client. Usually it's very straightforward. It's very easy to implement, but care should be taken here, because if you have a lot of events, a lot of updates happening in the cluster, you can overflow your client. So this is something that you should remember about.
Okay. And unless anyone else has any questions, it looks like we're done for today. Thank you, Alexei, and thanks everyone. Please watch for the email with a link to the recording and to the slides, which you'll receive in the next 24 hours. Thanks everyone. Have a good day.